So when we're dealing with document classification, one challenge is to see how to take a long text document with many words and feed that information into a machine learning model. So the process here begins with the text itself. For example, when we have a sentence like this product broke as soon as I bought it, I am not very happy. The first step is the transformation. So here in this part, the words are converted into a format that the machine learning model can understand. So this transformation step typically involves converting the words into numerical vectors, which represent the text in a way that allows the model to process it mathematically. Because think about it, the computer can't really understand just from the words. It doesn't understand what the word product means. It doesn't understand the word broke. So what you would do is you'd want to convert these words into some sort of a numerical format. Now, once the text is converted into this numerical format, it can then be fed into the machine learning model. This model, which has been trained to recognize patterns in the data and actually look at the different characteristics about our text and then be used to predict, for example, on some sort of an output. And in this case, the output could be something like classify the text into different categories, such as a positive review or a negative review. Now, this entire process allows the machines to take unstructured text and then to make sense of it by categorizing it into useful outputs. So whether it's something like sentiment analysis, spam detection, or any other type of a classification task. Now, it's important to get some of the terminology right just because it helps to avoid any sort of further confusion. So when we talk about document, what we're essentially talking about is each distinct text that could be a sentence, a review, an article, a book, depending on whatever the type of model is that you're building. When we're talking about the word corpus, the corpus refers to the entire collection of every single document. So, for example, say that you have a data set where you're predicting, for example, whether an email is going to be considered a spam or not a spam email. Now, one row in your data, for example, is one email. So that's what we refer to as one document. And every single word that's used for every single one of the emails in your entire data set, that's what we refer to as the corpus. So that is going to be our sort of baseline, especially when we're talking about these things in a lot more detail. So we'll first start by looking at a very simple bag of words model. Now, this is one of the most simplest models that are used in natural language processing to convert the text into a numerical format that the machine learning algorithms can understand. So let's take an example where we have three documents. Document one is that the patient has a fever. Document two is that the patient is healthy. And document three is that the patient has high blood pressure. Patient also has a mild fever. Now, the first step in the bag of words model is to create a vocabulary. So a vocabulary is essentially just going to be a list of all of the unique words that appear across all of the documents. So in this case, the vocabulary contains 13 words. Patient has a fever, is healthy, high blood pressure, and mild also, and patient. So in this case, patient appears multiple times. Next, for each document, we can create a vector with the same length as the vocabulary. In this case, the vocabulary length is 13. And each word is represented by a specific index. So what we would do is we would go through each document and assign a value of 1 to the corresponding index if the word is present in that document, and 0 if it's absent. So here we can see that document 1 is represented as 1, 1, 1, 1, and then zeros because the rest of the words are not there. Which means that basically this document contains the words patient has a fever, but none of the other words. Document 3 with more words is represented by a longer vector where more indices are marked as 1 to indicate that the presence of words like high, blood pressure, and mild. Now, this method is useful because it captures the presence or absence of words in a document, but it doesn't actually capture the order of the words or their context, which is one of the limitations. Or what if we just had multiple mentions of that same word? So yeah, there are a couple of problems with this bag of words model, but it is still a foundational approach that's used in most text classification tasks. Now, one sort of issue that we can get when we are dealing with the bag of words models is the creation of what's known as a sparse matrix. Now, this happens when we have a large vocabulary. So each document is represented by a large vector, and most of the elements in these vectors are zero. For example, a document might be represented by a vector like 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, and then 1, 0, 0, 0. So there are only a few positions that contain ones, indicating the presence of a word, and the rest are all zeros. So as the vocabulary grows, the vectors keep getting larger and larger and larger. And this increases the amount of space that's needed to store the data in memory. Now, since most of the elements in the vector are zero, we end up with a lot of wasted space, which is quite inefficient, especially for large data sets. Now, there are different ways in which we can solve this. So for example, instead of storing all the zeros, we only store the positions of the ones and the corresponding values. So for example, this sort of sparse matrix might also be represented as something like this, where we have 1, 1, 18 is a 1, and 32 has a 1. So this corresponds to the index in our list. So this maybe, for example, if this is like index, well, I guess this would be 0, but it's fine. We can just say that this is the first position, this is the 18th position, this is the 32 position in our list. And we're saying that everywhere else we can assume that it's a 0, and only in these positions we can assume that these are going to be a 1. So this approach can reduce the amount of space that's required to store and process a lot of this text data, and even allow for more efficient computation for NLP. Something else that we can do, especially when we're dealing with a large vocabulary size, is we can employ some pre-processing techniques. Now, this can make it a lot easier for the model to process our text a lot more efficiently. Now, one key step is something known as stop words removal. So stop words are words like and, the, a, are, and these words don't typically contribute much to the meaning of a sentence. So that's why they can actually be safely removed. So for example, in the original sentence, this is a text full of content and we need to clean it up. After we apply the stop words removal, this text actually ends up becoming this text full content need clean up. Now this reduces the unnecessary words and also simplifies the input. Another thing that we can do is we can cast the text to lowercase. So if you would have noticed over here, when we were creating our vocabulary, we had patient that was mentioned here, but we also had another mention of patient here. But now in the computer, these are two completely different words, but we know that they're the same words. The only difference over here is that over here the P is capitalized. Over here the P is all lowercase. And that's it. That's the only difference between the two. So something that we can do is we can make sure that we can cast our text to all lowercase, and this can also reduce the overall vocabulary over here. And it can also reduce the amount of duplication in the vocabulary. Another step is something known as stemming and lemmatization. And these are methods that we can use to help reduce the words into their base form. So for example, over here, words like running, ran, and runs can all be reduced to the base word run. And this decreases the number of unique words that the model would actually need to handle. Now we'll talk about the stemming and lemmatization here in a second, but the last thing that we'll talk about here is the normalizing text. So sort of it's just another way in which we can essentially standardize the different variations of the words. So for example, over here, we can see that there are all of these different words like tomorrow, 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 but they all mean the same thing, which is just tomorrow. Before which how you would write it in text is the normalized word is just before. OTW is converted into the normalized form on the way. These emotes are then converted into just the original word, which is just a smile. So these are some of the pre-processing techniques that we can use to help to clean as well as simplify the input text. Now this allows the machine learning models to focus on the most meaningful information while also reducing the overall computational complexity. So we did talk about stemming before, but stemming is a key pre-processing technique that we use in NLP, where the goal over here is to reduce the words to their root form by chopping off the prefixes or suffixes. So the process helps to normalize the word that share the same root, but appear in different forms. So for example, the words automate, automatic, and automation, they're all stemmed into automat, which simplifies the overall vocabulary. Now, stemming is typically a language-dependent process. So it involves a crude affix removal, meaning that it may cut off parts of a word that result in a non-standard base form. So here, for example, connect, connected, and connection, these all get reduced to the base form, which is just connect. So while stemming is effective in reducing the size of the vocabulary, it can sometimes lead to inaccuracies because it doesn't always respect the linguistic structure. So for example, compressed and compression, which we can see over here, are both reduced to compress, even though these words differ in terms of the meaning as well as the grammatical form. Now, despite these limitations, stemming is often used because it helps to improve the computational efficiency by just simplifying the text and making it easier for the machine learning models to be able to process the large amounts of text. Now, lemmatization is another technique that we can also use for pre-processing. And the goal here is, again, to reduce the word to their root or base form, which is known as the lemma. Now, unlike stemming, which chops off the word endings to create a crude base form, lemmatization maps the word to their proper dictionary form. So it makes it a lot more linguistically accurate. For example, verbs like am, are, and is are all mapped to their base form be. And the words car, cars, cars, and cars, they're all mapped to the base word car. So this reduces the complexity of the text while also preserving the meaning. So lemmatization is particularly useful for normalizing the inflected forms of the word. So it makes it a lot easier to process text without losing the grammatical structure. So for example, the sentence, the boys' cars are different colors, would be lemmatized to the boy car be different color. So this process not only simplifies the vocabulary, but also retains the original meaning in a way that the models can work with a lot more efficiently or effectively. So here we can see some tables of words that have been lemmatized. So lemmatizing converts words like troubling, troubled, and trouble to all of them to just trouble. And goose and geese are just converted to goose. Versus if it was stemming, geese would have just been converted to something like GEES, and goose would have been converted to GOOS or something. So that's the idea behind stemming and lemmatization. So now if we were to apply the bag of words model with the pre-processing techniques, we can see here that this process greatly reduces the vocabulary size and it makes the data easier for machine learning models to handle. So let's start with the original text that we had with 3 documents in our data. Document 1 is patient has a fever, document 2 is patient is healthy, and document 3 is patient has a high blood pressure, patient also has a mild fever. When we apply our pre-processing techniques, we can see here that now document 1 becomes patient fever because has and a are both stop words. Document 2 is patient healthy because is also a stop word. And then document 3 becomes patient high blood pressure, patient mild fever. So this greatly reduced the amount of text that we ended up with over here in our document. So because we were able to do that, we can then apply our bag of words model to convert the text into numerical values. So same process as we had before, we pretty much just did the same exact step. So we created the vocabulary or set of unique words from the documents. So words like patient, fever, healthy, high blood pressure, and each word is assigned an index. Now, for each document that we create, a vector where each corresponding index corresponds to the whatever word that we have here. So if the word is present in the document, we assign 1 to that index. If it's absent, we assign 0. Same as what we did before. And we can see here that now the size of the vocabulary, it went from 13 to now just 7. So we can apply these sort of techniques to help reduce the overall size of our vocabulary. So we understood the bag of words model, but let's take a look at something a little bit more complex. Now, the bag of words model, which we knew that we are always going to have issues with, for example, one of them is the word context issue. So it sort of means like how do we know what words are similar to each other? So if a user searches for heart disease, we might want the system to return a document containing heart failure as well, just because these terms are contextually related to each other in medical discussions. However, with the bag of words approach, the model treats the disease and failure as completely independent or unrelated items. So it doesn't know that disease and failure are two words that are pretty close to each other in terms of their meaning. So because the word disease and the word failure is just represented in a different vector set, these two are completely different from each other. So there's no connection or similarity based on these two words in the model because the vectors are one hot encoded and only capture the presence or absence of the words, not their meaning or relationship. Now, this can become a major limitation because the model can't actually understand that disease and failure could be used interchangeably in certain contexts. So to overcome this, more advanced techniques like word embeddings or contextual models are then used. And these can help to capture the relationships between words and their meaning based on the context that they're used in. So if we were to take a look, the one ideal solution that we can have is something known as word2vec. So word2vec was a revolutionary approach that was used to understand the meaning of the words based on their context. So it was based on this quote here by J.R. Firth, which says that you shall know a word by the company that it keeps. So in this method, the context in which the word appears is used to infer its meaning. So if we were to take an example, suppose that I want to understand the word cardiac, right? So in this sentence here, a cardiac arrest is when a person's heart stops pumping blood around their body and they stop breathing normally. The word cardiac appears near the word arrest, and it also appears near other heart-related terms like heart, pumping, blood, breathing, those kind of words. In another sentence here, many cardiac arrests in adults happen because of a heart attack. This is because a person who's having a heart attack may develop a dangerous heart rhythm. So in this case, the word cardiac appears near the words heart attack. We also see over here, it also appears next to dangerous heart rhythm. And we can kind of see, we get an idea based on like what are the words that are going to be very close to whenever this word cardiac is essentially being mentioned. So when we look at the words around cardiac in multiple sentences, word2vec can help determine that cardiac is related to heart and medical conditions. The essence of word2vec is that it doesn't just treat the words as isolated tokens. Instead, what it does is that it creates vectors that represent their relationships to other words. So it can actually help in capturing the similarities between the words based on their surrounding context. Now, this can help in finding synonyms. It can help in identifying related terms, or also in helping things like document retrieval. So over here, we can see that an example of a word2vec, right? It's very different from the bag of words approach that we have been looking at before. So it really leverages the context around the word to build the associations between terms. So from just the two sentences that we analyzed earlier, we can infer that the word cardiac is closely related to terms like heart, stops, pumping, breathing, adults, dangerous, rhythm. And this collection of related words provides a contextual understanding of the word cardiac. So in word2vec, each word in the vocabulary is represented with a vector. So the vector encodes the relationships between the word and other words in this context. So for example, the word cardiac would have a vector like this, where each value in the vector represents a specific dimension of the word's relationship to other words in the context of the training data. So on the right over here, we can see a visualization of the word2vec model that's trained on 150,000 PubMed abstracts. So this plot uses principal component analysis to reduce the dimensionalities of the word vectors so we can visualize the relationships between the terms. So when we look at, for example, words like neuroscience, like dopamine, GABA, and serotonin, these are all sort of clustered in together. So we can see that they're pretty close over here. It shows that Word2Vec is actually able to capture the semantic similarities based on how words appear frequently each other in terms of these sentences. So ultimately, the goal over here is that the vectors that are produced by Word2Vec allows us to predict that which words are likely to appear in similar contexts. So it makes it a powerful tool for tasks like document retrieval, for classification, and also understanding the semantic relationship between the words. So Word2Vec not only captures the semantic meaning, but also the relationships between the words in a vector space. So one of the most famous examples involves the vector arithmetic to show that relationships like gender, verb tense, and countries with their capital. So here on the left, we can see that the vector representing king and man, which is this vector right here, is similar to the difference between queen and woman. So if you look at over here, the size of this and the size of this, right, is going to be quite similar. And this can illustrate how Word2Vec actually captures the gender relationships. In the middle one, we can see the relationship between verb tenses. So the relationship between walk and walking is similar to the relationship between swam and swimming. Now, Word2Vec can detect these regular patterns through vector transformations. So another example over here, we can see that a country capital relationship. So for example, the vector connecting Spain to Madrid, which is over here, is similar to the one connecting Germany to Berlin, and Turkey to Ankara. So this example really helps to highlight one of the core principles of Word2Vec, where it can make inferences based on the relationships between the words. So for example, here we have an equation for the vector for queen is equals to the vector king minus the vector for man plus the vector for woman. Because king plus man equals to queen plus woman. So this type of transformation is what makes Word2Vec a powerful tool for understanding word relationships and also building meaningful representations of words in different contexts. So you might wonder now, how is Word2Vec trained? So Word2Vec is trained like this. First, we have to collect an input. The input, for example, is typically a large corpus of text, so something like Wikipedia articles. Now, the training process happens where the text is processed using the Word2Vec model, which is essentially a neural network that learns the vector representations for words in the corpus. So the model is trained to predict the surrounding words for a given word. Then, once it's trained, each word in the vocabulary is represented as a fixed size vector with dimensionality d as shown here. And these vectors capture the semantic relationships between all of these different words. So we would train on the entirety of Wikipedia, and then based on that, we understand what is the overall vector for heart. So anytime we get heart in our document, we know what the vector for that will look like. Anytime in our document we have the word liver, we would reuse the same vector for liver. So that's the goal here, is that we want to end up with the same vector that's trained on this series of all of these different articles on Wikipedia. So each word's vector is a unique representation based on its context within the corpus. And that's sort of the idea behind how the Word2Vec is trained. So for each document, we would begin by first taking the target word. So for example, if we were to look at the sentence, mitochondria is the powerhouse of the cell, we could take mitochondria as the target word. And this becomes an input to the shallow neural network. Now, using this target word, we try to predict the words that appear closest to the words mitochondria. So in this case, the words that we want to predict is the powerhouse of a cell. And then once you train the model to predict these related words, the vector for mitochondria is just the values that you would get from the hidden layer, after which you would move to the next target word, which is, and then you would go to the next target word, which is the, and then the next one, which is powerhouse, and then off, a cell. So all you're doing is you keep training the model on all of every single occurrence of each of these words here. And then comes the final step, which is actually going to be our document classification. So really, it's after we apply the word to vec, then we get a set of word vectors. And after we have the word vectors, we can then use our same exact models that we've been using this whole time. Random forest, linear regression, neural networks. The only difference in natural language processing is we have the additional step of converting the text into just a vector representation. So this is really the overall process of how the natural language processing workflow actually works.